Hello, everyone. Welcome to week four's office hours. I apologize for the delay on posting the link. I thought I'd already posted it last week, but it turned out I hadn't. So had to kind of quickly log in and do that this morning. Just a couple of quick announcements to go over. Just a reminder that as of September 15th, Google's getting rid of Google Hangouts on Air. So we're going to be switching to doing YouTube live streaming. Shouldn't be very difficult to set up at all, but just the format will change a little bit. Other than that, everything else is going to keep going the way it is for the office hours. As for this week, so far we're about halfway through the unit on extending other models that other people have written. We should be, all of Unit 2 is up and posted, and so you should be working through that. I should have most of the rest of Unit 3 up today or tomorrow, basically, and so that'll be available as well at that point. I think that's about it for now. When it comes to the project in the near future, I just wanted to quickly mention this. We're going to have a design document kind of turn in probably when we are doing chapter 4, so unit 4 next week. And during that time, I'll have a document that you'll be turning in and then peer reviewing. We're still working out all the details on getting peer review set up on the Complexity Explorer website, but it should be ready to go for some time about the end of this month, beginning of next month. So that almost perfectly coincides with Unit 4, and so that should work out well. Other than that, I think, at this point, we're kind of into the what is NetLogo, not what is NetLogo, but how do you write code in NetLogo? How do you program NetLogo? How do you start to build up these agent-based models? And so hopefully you're starting to get a flavor for some of that as we go along. We got at least one person on the line this week. So John Villaraga, right?
Yes.
So John, do you have any questions about the class?
I have a question, but it's not like just for this week. It's more about like the overall agent-based modeling.
That's fine. Go ahead.
I was just wondering, how do you know that your model is right when you don't have any data for it? You know what I'm saying? Like, how can you validate that? Oh, I know that this might be the that will come up from this system. You know what I'm saying? Because from my experience, I'm very used to use I either have data that I got from the lab, or I have just historical data, and then I build the model with that data. You know what I'm saying? With agent-based modeling, it's just I'm still trying to grasp the concept of how can I actually validate my model? How can I actually say oh, I know that this is correct?
Right. Well, so that's a fantastic question. And in fact, when I first came to the social sciences from computer science, that was one of the questions that people asked me quite a bit, was how do you know that these models that you're building of social phenomenon are actually correct, or actually robust and rigorous in some ways, right? And so I think you use the word validate quite a bit, and I think that's an important component of it. I do think there's another aspect that we often talk about in computer science that maybe is not as well understood in other disciplines, which is verification as well, right? So before, and we'll talk about this a lot in unit, I believe it's unit 7 of this class, right? But we'll talk about both verification and validation. I think that those are the two critical components of making sure your model is correct in some sense. So verification is the process of making sure that the model you actually wrote corresponds to the conceptual model that you have, right? And so that's, for instance, making sure that that the way you designed the model is the same as the way you implement it. Now, one easy aspect of that is making sure there are no bugs, right? Making sure that you didn't do anything incorrectly. But a more complicated aspect of that is also making sure that kind of the algorithms that you're thinking about for creating the execution of the agent's actions actually are the same as what you think they're doing, which may seem like it's an easy task, but it's not always as easy as you might see, which is why, as you'll see as I'm developing code in this class, I often run a bunch of spot checks as I'm doing the code to actually check to make sure. So verification aside, that's one aspect, right? The next question is validation, right? So now let's imagine that you have a model, an agent-based model that you've constructed. You believe that it, in fact, is doing what you think it should be doing, so it is verified to some extent, right? And then the next question is, how do you make sure that that model tells you something interesting about the real world? And that's what we call validation. In other words, how does the implemented model correspond to the real world, right? And you mentioned some types without data. Now, I think that there's multiple ways agent-based modeling can be used. One is without data for sure, but one is with data. So let me talk briefly about that, since that didn't seem to be the focus of your question, and just say that, and a lot of agent-based models are compared directly to data, right? So we take the input parameters to the model, we try to make sure they correspond to some real-world input parameters, and then we take the output of the model and we do some sort of statistical tests to show that it has some relationship to real-world data, right? So for instance, one of the models we'll probably talk about in the near future is a version of the new product adoption model that's used a lot in marketing called the BAS model. And in that model, what the output is the amount of products adopted per year or per quarter, for whatever time scale you're thinking about for a new product, right? So one thing you could do is you could set up the model with some sort of parameter settings that correspond to real world parameter settings about things like advertising and word of mouth influence. And then you could see if the predictions match real world data sets. Right? So that's the easy one. That's the empirical validation kind of way of thinking, right? But there is a good argument. In fact, I posted a tweet about it. John Howland, who is one of my advisors and who passed away last summer, he actually was a big fan of what he called exploratory modeling, right? And here the idea is that we essentially create a model to see if a set of conditions can create a phenomenon we're interested in, right? So think about the Boyd's model, for instance, right? You could build the Boyd's model without ever kind of in a traditional sense of comparing the results to the real world, right? You could simply write the rules and see if the patterns of behavior reflect those of what you think flocks look like, right? Now, I would argue in some sense that you are doing an implicit empirical comparison there, right? You're comparing the flocking patterns to your image of flocking patterns that you get from the system. And so I do think there is a form of validation that goes on there. But I think a lot of times in these exploratory models, the validation is the validity to the extent to which it helps you or someone understand the phenomenon you're interested in. So this actually brings up one last point I'll make, and then I'll see if this makes sense to you at all, John, which is that validity is not a binary question, right? A model is not valid or invalid. It's shades of validity, right? One model could be validated to a larger extent than another. And to that extent, the most important kind of threshold for validity is whether or not you've met the validation of the community that you're talking to, right? Is the model valid enough for that community? And when you're doing exploratory modeling, that level of validation is going to be very different than, say, when you're doing kind of a point forecast model for demographics or something like that. So does that help at all when you're thinking through this?
Kind of, yeah. I'm still processing because I'm very used to for example, build machine learning models. As I said before, also for example, using experimental data and probably put all the data into like a package. They'll build a model with that.
Mhm.
But with this, it's more like I feel like I'm generating the data from the model. So it's like, oh, that's what I think. I'm not quite sure about that,
Mhm.
but that's how I think about it. It's kind of like the opposite of what I've been doing.
Yeah. I think you're very right. Right. So I think that and it's kind of interesting to me because when I think of modeling, maybe because I came from a computer standpoint as opposed to a statistical standpoint, right? I think of a model as something that makes a prediction about the future, right?
Yes.
That says that given this set of data, this is what the future is likely to have, right? Or this set of inputs, right? Whereas I think this, a lot of times people who are brought up more in a statistical tradition think of a model as something that describes a data set you already have, right? And agent-based model in this context, I think, is often primarily used in kind of this like prediction, forecasting, exploration kind of way, right? It's going to provide you with some insight into what the future might look like if you set the parameters of the model in this way, right? Now, that being said, I do think you can use agent-based modeling in the exact same sense that we use it in a statistical framework setting, right? So let's imagine I have a bunch of data about a particular phenomenon. A lot of times in statistics, we propose a model, right? And when we propose that model, right, or this could be machine learning too, it doesn't matter, right? We propose a model as to how the different elements interact, what features might be relevant in the machine learning framework, right? And then we fit that model as well as possible to the data we have in hand, right? You can do that exact same thing in agent-based modeling, right? So I can take a set of data, I can propose an agent-based model that will generate that set of data, and I can then calibrate the inputs to the agent-based model to exactly match that data as well as possible. And we haven't really talked about that yet. We'll talk about that in later units in more detail.
Okay.
This actually, in NetLogo, this is actually fairly easy to do, thanks to a particular software package that was developed by a student of mine, actually a student of Uri Walensky's, but I was jointly advising him at the time, for Stonedahl. He built a tool that's not part of the regular NetLogo package, but if you Google it, you can find it, called behavior search. And behavior search is similar to behavior space, which we'll talk about, but it allows you to use machine learning or another statistical method to minimize the difference between a model's output and real world output to find the best set of parameters to fit that data, right? So I just want to make it clear that you're very right. In many cases, when we say agent-based model, we mean, can we write a set of rules such that the data it generates corresponds in some way to the real world, right, or provides some insight about the real world. But you could do it the other way. You could take a set of empirical data, write the rules for an agent-based model, and then calibrate that model as soon as possible to the data.
Okay.
Yeah.
I have another question.
Yeah.
Since agent-based modeling just give you like an emergent pattern, and is usually always randomized, so it's gonna sometimes it just gives you like similar emergent patterns, but not the same one. Then like, what if you're trying to find like the optimum emergent pattern? How can you, because like if there is an optimum, the other ones would be like local minimums.
Right, for sure.
So is there a way to I don't know, like probably add another algorithm inside the agent-based model, or just use the agent-based model on its own and just like be like, oh, give me the best emergent pattern or something like that?
Yeah, there's quite a bit of work into this space. So you're talking about like just quickly to make sure we're on the same page, right? Like,
Yeah.
imagine I have an ideal flock, right, where all the boids are exactly in a certain radius around the center. That's kind of you're trying to find that kind of situation, right?
Yes.
Yeah. Okay. So so there's been a lot of work on what I would call multi-agent systems engineering, which is exactly in this space, right? It's trying to identify or engineer a set of rules at the lower level that creates an emergent pattern exactly at the higher level that you're interested in, right?
Okay.
And the community, the community, and we talked a little about this, I think, in one of the previous office hours. Yeah, we did. When we talked about conferences or agent-based models. There's a community called AMOS, which is Autonomous Agents and Multi-Agent Systems. And they spend, a lot of the people there spend time thinking about this, right? So for instance, they might ask, like, if I was to create a bunch, this was partially inspired by an old advisor of mine, not that he's that old, but he was a previous advisor of mine, Mike Wellman at the University of Michigan. He did a bunch of work on trying to figure out ideal rules for economic agents, such that you can get some particular outcomes, emergent outcomes out of them. Right? And so that's the kind of space that they often operate in. It's trying to figure out how do I write rules such that I obtain the emergent pattern that I want to see out, right? Agent-based modeling, that community is definitely related to the multi-agent systems engineering group, right? In many ways. But it's kind of a different approach somewhat, right? Multi-agent systems engineering often wants to force a particular outcome, like you said, right? Whereas agent-based modeling, or not force, but achieve at least a particular outcome. Agent-based modeling is often being used to describe a phenomenon you're seeing around you instead, right? So a lot of times when you see agent-based modeling versus multi-agent systems, that's the primary distinction between the two, right? Now, they're sometimes used interchangeably, right? But I think that a lot of times people who are using the phrases multi-agent systems are often talking about the engineering component. People using agent-based modeling are talking about the other way. I know of several papers in that space that specifically are trying to solve kind of the global problem of, given a pattern, an emergent pattern, what are the low-level rules? I don't have them off the top of my head right now, but I could definitely, if you shoot me an email or tweet at me later, I could definitely send you a couple of references while I'm on this.
Okay, that would be great. Wait, so multi-agent system is like the same as agent-based modeling, it's just that you can actually find like the optimal solution, I'm assuming, or because from what you said, agent-based modeling just sounds like you just want to see what's the behavior of this system, but it's not like you're actually interested in finding a specific answer or like the best solution.
So this boundary is very blurry. Let me put it that way. First of all, right? I would say that people who tend to use the words multi-agent systems tend to come at it from more of kind of an engineering background, right?
Okay.
Whereas the people who tend to use the words agent-based modeling tend to come at it from more of a descriptive or scientific understanding as opposed to optimal control kind of approach. Does that make sense somewhat?
Yeah, I understand.
Yeah. So I mean, but that being said, you find people in both communities who are trying to do the thing that the other community is talking about, right? So it's not a hard and fast rule. I'm just saying that in general, that's the case. I would still argue that one thing that you said just seemed a little off to me, which is that in agent-based modeling, a lot of times still the goal is to find a optimal outcome, but the optimum in this case is defined to be an outcome that best matches the empirical patterns of data that we see, right? As opposed to an outcome that achieves something that we think that the emergent system should be. Does that make sense at all?
Yes, I understand.
Okay.
So does a NetLogo support this? I'm assuming it doesn't.
I mean, so I would say at this point, what we're talking about is not necessarily the capabilities of the software. What we're talking about is the way you're using that software. And I would say NetLogo is more geared towards agent-based modeling and less towards multi-agent systems and engineering. But but you definitely could use it for multi-agent systems, right? Like when I think of multi-agent systems, I think of things like the SOAR package, which comes out of the University of Michigan, and ACTAR and things like that, which are more meant to exist to let you craft rules to achieve a desired outcome, as opposed to modeling a phenomenon you see around you, right? Again, if you want some particular references to those software packages, I'm happy to send them to you or put them up someplace.
Oh, thank you.
Any other questions, John?
I was going to ask you, in NetLogo, are the patches like the kind of like the, how do you say, the environment where the agents are interacting with each other? I'm kind of like confused with what the patches, because I understand the turtles are the agents, but the patches are in the background. But what do they do? Like, what can I do with that?
Okay, so the patches, the patches are meant to represent a static environment, right? And so one way to think about the patches is that they're, a very primitive way to think about it is they're the exact same things as turtles, except they don't move, right? And they represent, and they take up space. Turtles actually don't take up space either. They're infinitely small points, right? Now, we see them in the visualization as taking up space, but in reality, they're represented by a point, right? To that extent, I definitely think the way you should think of patches a lot of time as some sort of environment that the turtles are operating over, upon, or on top of, right? And this will become a lot more clear when we start talking about more realistic environments for NetLogo. So we're going to talk about how to bring in GIS data and how to look at actual kind of real world environments, if you will, that NetLogo operates in. I should say that when NetLogo was first created, and when a lot of these agent-based modeling packages were first created, there was a big emphasis on spatial interactions, right? Just because that was very hard to do in a lot of traditional modeling frameworks, right? Nowadays, so agent-based modeling was created in the 90s, roughly, right, in its modern form. In these, that you see some of the work of Steve Strogatz and Duncan Watts and others that really start to talk about the power of large-scale network data. Now, there was great work before that from sociologists about networks like Grant Vetter and Harrison White and them. But it was really at that point that you saw the advent of social networks as really kind of this, determining the interaction structure of individuals. And so I think there's been a move since the early 2000s to worry less about physical interactions for a lot of modeling frameworks and more about social interactions, which is why the patches have become somewhat less important, but there's still a lot of modeling frameworks out there, such as spatial models, where they're very important.
Okay.
Does that help?
Thank you. Yeah, thank you.
So we had a couple of questions. Did you have any more questions, John, or are you?
Not for now. Thank you.
Okay. So there were a couple of questions that got sent in ahead of time, so I thought I'd talk about some of them. So one of them was about from Min, about where that said that my question for this week concerns bringing about a desired feature of a model. So this seems similar to some of John's questions. In the case of my project, it is modeling the role of social networks and how they might contribute to the proliferation of altruism or selfishness. I have in mind that as one of its features, my model should capture the physical reality of decisions made at time step t=n, and should be dependent on the n-1 decisions before made on the part of the agent. So my question in general is, if you have some complex phenomena in mind, the insist should be a property since it is physically observed and therefore motivated. How do you go about determining the simpler rules at the agent level that will generate the complex behavior at the aggregate level? Thanks for putting up your time. Yeah. So, okay. So I think this is almost exactly the question John was asking, right? Which is, given the fact that I have some emergent pattern, how do I make sure that my low-level actions give rise to that emergent pattern, right? And I think that this is, in many ways, this is the art and science of agent-based modeling, right? It is the idea that you need to design your rules such that you generate that data. And I don't know, there are, and I'm happy to share. I know there's a couple of papers out about simplified problem spaces where people have shown that, if you have this emergent pattern, then here's a procedure that will optimally guarantee you a set of rules. But these are extremely simplified. Like one of the examples I'm thinking about is in the case of origami, right? It's like, what are the rules that you could use for agents who are deciding whether or not to fold individual parts of paper to create a pattern of behavior, an emergent pattern that is the origami object, right? And so in these simplified cases, sometimes you can guarantee that the low-level agents will create the emergent level pattern. In the general case, I don't think there is a way to do that, right? As far as we know, there's no way to say that these low-level rules, that given this emergent pattern, these are the low-level rules that will create that emergent pattern. And I would argue that in many cases, that's not what you necessarily want either, right? The truth of the matter is that we know, except for a few, well, I would say in almost every case, we know that the emergent patterns are an outcome of low-level interactions, right? And so therefore, you don't want to take an emergent pattern and force low-level rules from it. That is what we would sometimes call a reductionist mindset about how you might create the agent level rules. What we instead want to do is we want to propose a theory of low-level rules such that it generates the pattern of higher-level rules that higher-level behavior that we're interested in seeing, right? That is what is emergence, right? That is the goal of an emergent property, and so that's often what we're searching for. So now that being said, right? Let's say you have some hypotheses about what those low-level rules might look like, and you want to ask the question, which high-level rules, or sorry, you want to ask the question, which best matches the high-level data that I have about this phenomenon, right? That, I think, is a very valid question, right? And in that case, I think you can use some of the methods that we'll talk about in later units in the class, where you do statistical testing between the output of the model and the empirical data that you're seeing to try and determine what's going on. I've mentioned a couple of them before, things like likelihood modeling, right? Or doing some sort of just minimum distance between output data and real world data and things like that can help you adjudicate how well a model does at generating those emergent patterns. So thanks for the question, man. I hope that helps you think through a little bit of what's going on there. Feel free to send me another question or a follow-up question if that doesn't quite get to it. Gustavo actually had sent me a couple of questions about exporting data, and since I thought that those might be useful to the larger class, I thought I'd take a quick second to kind of respond to them here. So some of it had to do with trying to export data directly from NetLogo. He asked in the examples from Unit 2, is there a way to export patterns that are not raster-based images, but vector-based images? So many of you may have discovered already in NetLogo that you can export an image directly by right-clicking on the screen and just selecting Export World or Export Interface, right? But what if you want to actually export? So, for instance, in the Unit 2 example, in the heroes and cowards, you want to export the vectors between the individuals. The easy answer to this question is that there isn't an easy way to do that, right? The harder answer is that essentially you could, because NetLogo is like any piece of software package, Turing complete, you could write your own code to do this, right? So you could write a code that basically grabs all of the locations of the different turtles and the lines connecting them, and then writes them out in a vector-based file format, right? That's not easy, but you could do it. Unfortunately, I don't think, as far as I know, and there is an easy way to do that. Maybe there's an extension out there in Netlogo. I haven't seen one along those particular lines before, but I could be wrong. I don't know all the extensions out there. So Gustavo also asked, I'm also interested in reconstructing individual path behaviors in both 2D and 3D. What is the basic way to do this? Is there an example to demonstrate this, a package that makes this more accessible? I mean, one easy thing that you could do, right, that might not quite get down to what you're interested in doing, would be to use the pen in Netlogo, right? So you could have the agents place a pen down and then allow them to move the pen down, and that will give you some insight into the 2D patterns of behavior. Trying to get exact data about every agent's movement is a little trickier. Again, I think you'd wind up having to write some code that, for instance, at the end of every go step, just outputs the XY coordinates for every turtle and their orientation or something along those lines, right? I think that's all you need to reconstruct the 2D or 3D model behavior. But I don't think that there's a package that automatically does that for you that I know of. I can look into that a little bit more. And finally, how can a researcher approach studying the space distributions of different agent behaviors in software? What statistical strategies and or implementations in Netlogo can be used for this purpose? So I assume, Gustavo, this one confuses me a little bit more, but I assume what you mean by that is how can we best record the data about different distributions of spatial agents? In other words, how can we, for instance, map where agents are likely to be in that space given a particular model, right? That's a tough one. That again, unfortunately, I think the answer is going to be that there is no inbuilt way to do that. There's no way to just say, observe all the agents' behaviors and write down the spatial distribution of their agents over time. What you could do that I think would be an easy approach to it, right, would be to have every patch in the model just record at every time step how many agents are within that patch. And then you could dump all that patch data at the end of the model. And that would essentially be a spatial distribution, right? That would be the easiest way I could think of to do something like that. Of course, you could go more fine-grained than that. And by the way, you could go more fine-grained by that just by using that approach. You could just change the number of patches in the model and how big the patches are, and you could get more fine-grained results right off the bat. So that's the easiest way I can think of to do that. I don't know of any software packages out there that do that automatically. So thanks for the questions, Gustavo. Those are great. Gustavo also sent a nice follow-up email. If anyone wants to try and implement or tries to work with the Netlogo model, the Ashe Netlogo model that Marco Jansen talked about, and this is something I should have mentioned, you do need to, it's up on OpenABM, and you do need to create a folder to place the data files into. So inside of your, inside of that folder, you want inside of wherever the model is, you want to create another folder called data and place all the .asc, the ASCII files into that folder. And that should make it work. That's because in the Netlogo code that Marco's written, there's actually a direct call to the data folder. And so you could either change the call in the Netlogo model to point to wherever you put the data files, or you can just recreate what they put in for the data files. So thanks for those questions and for that comment, Gustavo. That's great. Okay. We do have a question in the Q&A from Jerry Catilius. Jerry asks, would you expand on differences of a model of individuals versus groups? Example, Schelling's model is households, not individuals of different colors. Thanks. Yeah, so this is a great question. So one of the question, and we'll get into this right when we get into Unit 4, so next week. One of the questions you first need to decide when you think about building your own model is, what is the scale of my model? And one of the aspects of that scale question is, what is the resolution of an individual agent, right? And so in this question, what you're really asking is, how much does an agent represent? Does an agent represent one individual, 10 individuals, 100 individuals, right? And I think that the question really depends upon, you're gonna hear me say this a lot, but the answer to that question depends upon the question you're asking about the model, right? So in Schelling's case, right, he was interested in segregation patterns. And segregation patterns are patterns that exist at the household level, not really at the level of the individual, right? And so therefore it makes sense to build that model at the household level, right? In another example, in actually the work that I've been doing with Manuel Chica right now, we build a social network. We actually build a social network where each individual roughly represents 2 to 3 individuals, 2 I think in most of the models that we looked at, right? And the reason why is because we found that scaling down in that way allowed us to still model the outcome of policies on the network without giving up too much resolution to the overall model, right? Now you might say, well, that's kind of weird because you actually have a social network, and each social network you get these 2 individuals. But in fact, in many social networks, we get tight cliques of individuals that are almost indistinguishable. They act almost as a single unit, right? And so this assumption is not a terrible assumption for that. The reason why we chose that level is because of the fact that it's simply the computational power needed to generate results for that model went down significantly by having the number of agents in the model. And so therefore we could run a lot more simulations than we originally intended to. And so that was the reason why we made that choice. But I think that a lot of times, and this is something we talked about at the very beginning of the class, right? Your choice of how complex an agent should be is related to this question about the individuals versus groups, right? And so to that extent, it's affected by things like the amount of computational power you have, the complexity you want to put into each individual, right? And essentially the question you want to ask, what's the appropriate unit of analysis for the question you want to ask? And by balancing all those 3 questions together, you can kind of start to understand what the appropriate level of modeling is. Agent, by the way, is the reason why I always use the word agent-based modeling and not individual-based modeling, right? Is because individual does have a strong connotation of being a single individual, right? But agent is just an agent of action, right? And it's not necessarily a single individual. It could be a household, it could be a company, it could be a nation, right? And that's really what we're talking about when we talk about an agent. So great question, Jerry. If you have any follow-ups to that or any other questions you'd like to share, feel free to shoot them along. Okay, so let me just scan real quickly through the Twitter stream, see if there's anything up there or anything along those lines. Otherwise, I think that's it for this week. Yeah, okay, yeah, I think that's about it. Some people, I see a couple of tweets about people playing around with the L for all model and so that's been everyone. Any other questions? John, anything last words from you?
No, I think I'm good for now. I was just gonna ask you if you can probably send me the references that you mentioned.
Sure. Can you shoot me an email to remind me, just because otherwise it'll slip my mind. Just email me at abm@complexityexplorer.org and I'll respond to the email there. And then I'll also post it up on the discussion forums as well.
Okay, so you said to which email you said? The agent-based modeling or the complexity explorer?
complexityexplorer.org. Okay. Yeah.
Okay, thank you.
Otherwise, I have a tendency to forget these things. So, but I'm happy to do it. Cool. Thank you very much, John, for joining me. And if there are any other questions from the audience, I'll go ahead and shut down the Hangout for today. Just a quick reminder to recap what I said at the beginning. Google Hangouts on Air is ending, so we're going to be switching to YouTube live streaming in the near future. That should be, you should not notice any difference. One thing is I don't think they have the Q&A app there, so we may have to rely more on the Twitter stream for getting questions or email. The other thing, let's see, and yeah, we're working along Unit 3. We just wrapped up Unit 2 on the heroes and cowards model. I hope you enjoyed it. Unit 3, we're going to talk about extending the model. And next week is Unit 4, which is probably my favorite unit. It's in fact what the textbook was written around, Chapter 4, which is also Unit 4, right? Which is basically step-by-step instructions of how to create an agent-based model from the ground up. And so that's really kind of everything that we've been doing has been leading to this, and everything after we'll be talking about that process in more detail. So thanks everyone for joining in. I hope the class has been enjoyable. Let me know if you have any questions or concerns. I'll probably be posting a feedback survey sometime in the next week or so about how fast the class is going. Are we going too fast, too slow, and any particular topics people would be interested in, just so I can kind of keep the class moderated to your interest levels. Thanks everybody, and thanks John for joining me. Take care.
Okay, thank you.